Hi everybody, today we're looking at growth and decay. Exponential growth can be shown in many real-world scenarios. Cases like population growth, either for people or bacteria, infection rates, disease passing through a population, or in compound interest type cases. In each of these cases we have a time t, some value that's changing, and y0, the initial population, or the initial infection rate, or the initial amount being invested, and some sort of growth factor or a decay factor. If it's a growth factor, a will be greater than 1, and if it's a decay factor, it'll be between 0 and 1. So we end up with this equation here. Yt equals y0 a to the power of t. And here we hit our first little hurdle, in that we need to be careful when we interpret y0. Because y0 has to be the initial value at the start of the 0th year. And y1 occurs at the start of the next year. So if we want the solution at the end of t1, we're actually seeking y2, not y1. Similarly, if we're finding a and we're given y values for non-consecutive values of t, we must take the nth root where n is the difference in t values. So all this is lots of words. I think it's probably time we had a look at an example. So we have this table of values. Something's going on in 1995, 1999, and 2002. And we could just as easily label that x value there t, so I might just do that just to make it consistent with what we're talking about. And whatever it is that's growing, because we can see it's growing, it's gone from 2000 to 2207 to 2377, we believe is increasing at a growth rate of about 2.5%, because that's what it says in the next part of the problem. So the first thing we need to do is to have a look at these three values. Now they're not incrementing one at a time, so we've got a bit of a problem here. The growth between here and here will not be the annual growth rate. So to start with, we'll look at it and we'll say, all right, well there's 4 years between here and here. That's the difference. So it must have compounded 4 times between these values. So we can stick that into an equation. If we start with, where did 2437 come from? Oh, poop. That should be 2207. Let's fix that up. It's always important that you check what you're writing. 2207 equals a to the 4 times 2000, which is just the equation above with the values put in. So, and this is probably back to front to how we'd normally see it. We'd see it as 2000 times a to the 4. Okay, so that formula there is just this one up here. That's the finishing value, that's the initial population, that's the growth factor, and that's the period of time. So we know that after 4 compound growths, actually I've probably still got this sitting in a table over here, I might bring it up. Here we go. Here's that scenario with 1.25%, with 2.5% growth factor starting at 2000 going to 2015. And we can see that we've applied 2.5%, I think this is 20 times, once, twice, 3 times, 4 times, 5 times. And in our case, we're starting from 1999 and we're going to 1995. So 1999 up to 1995 up to 1999, 1, 2, 3, 4 compounds, which is where that number there comes from. But we don't know that. That's just a table that I made up to make up the problem. We've just been given this information. So we can solve this, and that will tell us the growth rate, because we can solve for a with our calculator. A to the 4 equals 2207 divided by 2000, dividing both sides by 2000. Take the fourth root of both sides, and that will give us 1.025. And away we'll go. So there's our first one. And 1.025, we should know, is 2.5%. And the one in front indicates that it's increasing by 2.5%. If it was 0.9975, that would indicate that it's decreasing by 2.5%. Anyhow, let's check another one. So we can go from 2002 back to 1999. To make life easy, this time I'm going to declare this my starting value and say that it's increased by 3 years. So A equals the cube root of that divided by that. I've just done this process in one step. And again, I get 1.025. So from these two sets of values, I can see that the annual growth rate was 2.5, and that's actually a continuous set from 1995 to 1999, from 1999 to 2002. So over the entire period, the growth rate's been 2.5%. Now once we have that, find the value of y if x equals 2008 with a similar growth rate. So from 2008 to 2002, which is our next nearest one, there's 6 years apart. Y6 equals 2377 times 1.025 to the power of 6, which gives us 2757 when x is 2008. Now, this approach may seem strange because you might want to put y0 here every time, but because we're compounding by a fixed rate, it doesn't really matter where we start as long as we go forward from that point. It's a feature of growth and decay. So, let's look at some simpler examples. That's probably the most difficult one we'll do today. Question 1. $20,000 is deposited at 5% per annum, calculated monthly for 2 years. Stick $20,000 into the initial amount. Now we've got to be careful because it's calculated monthly, so it's going to compound every month. So we're going to have 24 compounds, 12 each year. So T will be 24 when it's finished. But if the annual rate is being calculated, to find out how much interest is done per month, we're only going to divide by 12. So our A value is going to equal 1 because it's increasing, plus 5 divided by 12, the interest rate per month, divided by 100 to make it into a percent. Stick that in here, repeat it 24 times, and we'll get, at the end of 2 years, we'll get $2,098 of interest. And we'll have $22,098 and a bit in the bank. Question 2. 2 million bacteria are treated with a drug that kill 4% every hour. How many bacteria remain after 3 days? Our initial value is 2 million. Because it's done every hour, we'll get 3 lots of 24 over 3 days, which gives us 72 hours. A will be 1 minus 0.04. 0.04 is 4%. And because it's decaying, it'll be 0.96 of what was there before each period. So we set up our formula. Y72 will be equal to 2 million, hopefully that is 2 million, yep, times by 0.96 to the power of 72. So after 72, after being the drug every hour for 72 hours, only 106,000 bacteria will remain. And it's a good idea to round it to a reasonable number because there's no way that that exact number would be able to be counted. Question 3. At the start of 2008, the population of Rubyland was 253,000. The population grew to 350,000 by the end of 2008. Very popular land, this Rubyland. If the population grew exponentially, what would the population be by the end of 2020? So we have our initial value at the start of Y0, That's 253,000. Now, it grew to 350,000 by the end of 2008, which is the same as the start of 2009. So that would be Y1. So we can work out the growth rate, which is 1.383, by dividing the two values over the year. And we want to know by the end of 2020. So 2008, 0, 2009's 1, so on and so forth. We get to 2020 as t equals 13. Be really careful with that value. Take the initial value of 253,000, multiply it by the growth rate, raise it to the power of 13, and we get 17,196,431. Rubyland would be very packed by the end of 13 years if that growth rate continued, considering it only started with that 253,000. Question 4. Alex borrowed $5,000 on a credit card and did not repay it for 24 months. No, not Alex, Alexa borrowed $5,000 on a credit card and did not repay it for 24 months. If the interest rate is 29% per annum calculated daily, how much extra will she owe? Well, she starts with $5,000 that she's bought her color TV with. And the number of periods would be 2. There are 365 and a quarter days in a year. Multiply that by 2 for 2 years will give us 730.50. The annual growth rate is 29%. 29 divided by 100 divided by 365.25. That'll give us the daily growth rate. And then we'll find y 730.5. Now you could make an argument that it should be 731, but I haven't done so here. 5,000 times 1 plus 29 on 100 divided by 365.25, all raised to 730.5, gives you $8,928. So she will pay an extra $3,928 extra for not repaying her loan after 2 years, which is a good reason not to take out a credit card. Okay, well there's some examples. I hope they helped with some of the different types of growth and decay problems you can find. There are obviously many more, and we'll be looking at different ways with technology of solving these problems in the next exercise when we do APs and GPs, or specifically GPs. Thanks everyone.